When it comes to synthesis and multi-step reactions, you'll probably be shown simple examples in class, and then you show up to your exam, you have something like this. What is the first step? What should be your thought process to even begin with a problem like this? Here is what I typically see. Students will start with the reactant. Students will start with the product, meaning they'll start with the reactant and just go. Start from the product and just go that way. Or I've seen students who will actually write everything down and hope that somehow, some way, along the way, you're going to come up with the answer. Starting with a reactant, nope. Product, nope. Writing everything down, definitely nope. Now, here's the thing about synthesis compared to all the other reactions that you've done so far. Up to this point, you learned a specific topic with a specific reaction, and you were told, given molecule A, synthesize molecule B. And you knew in the alkene chapter, you do an alkene reaction. In the alkyne chapter, you do an alkyne reaction. You had to fill this in, or if you were given the reagent, you had to fill this in. But it was pretty straightforward. You knew exactly what to do. Now that you've learned many different reactions and you have to put them all together, the problem is going to look a little bit something like this. And give me hearts in the comments if you think I'm not exaggerating. Here is molecule A. Somehow, some way, in the time constraints of your exam, show me all the steps and reactants and intermediates that it's going to take to get to Z. And you have to come up with this one and 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 this one. Am I exaggerating by much? I'm exaggerating just a little bit. The problem with something like this is when you have so much to pull from, your mind will typically, well, if you don't get overwhelmed to begin with, for me, my mind would go blank. And I go into this like panic mode where I don't actually know what to do. I don't know the answer. I don't know where to go. I don't even know what to think. It's like my brain shut down. And you cannot afford to have your brain shut down on the exam. So what I want to show you is a way to simplify it, where instead of just going from A to Z, what if we can find a way to say, I can go from A at least to B. Let me go one step forward. And then maybe I can backtrack from Z to Y. I still have quite a few steps to go, but it's not as overwhelming. And then what if I can then find a way to go from B to C and from Y back to X? The more you can think logically from the beginning and the end, the more the entire reaction will come together in the middle, the more likely you are to get it right. If you have the right questions to ask and the right approach, rather than just going all over the place and being overwhelmed and not knowing what to do. So if you'd like me to show you how to do this without panicking, no, I don't want to insert an ad. So if you'd like me to show you how to do this without panicking, let me see some thumbs up in the comments. And I'm going to show you a very, very simple way that you can just jumpstart your brain. And instead of trying to figure out the next step, instead of trying to just answer it all you have to do is ask yourself these two questions. So let me know if you're ready to memorize just two questions that will help you snap out of it. Question number one, what's the same? And question number two, what's different? Instead of trying to analyze everything, we're just looking at what's the same and what's different. And specifically, I'm looking at a couple of different areas within the reactant and the product. And the point of this is to jumpstart your brain by giving you busy work, because easy, busy work is not hard to think of. It's very easy to go count the number of carbons. What is the functional group? And once your brain starts to move along, once your brain is already answering some questions, the rest kind of fall into place. And so what you want to look for in terms of what is the same and what is different are the number of carbon atoms on your chain. Did it grow? Did it shrink? Do I have to add anything? Do I have to change anything? The functional group, or whatever the group is. So for example, if you see a halogen, for the sake of this discussion, we'll call that a functional group because it's something on the molecule. And the position of reactivity, where on the molecule is this taking place? Meaning, do I have to move the functional group at any point? So far, if you're with me on these two questions, let's start with a very simple problem to demonstrate how to use this. So we're not going difficult just yet. I want to kind of work our way up to harder problems by looking at something like this. What do you think? Easy, medium, or hard? If you are just joining or watching the recording, welcome. For a copy of tonight's session notes, practice, and more, go to the pinned comment or leahforsyth.com/orgolive, and you'll get an email with the PDF and so much more. So let's start with the two questions. Question number one, what is the same? And question number two, what is different? We'll start with the number of carbons, where I'll make carbon 1 the side of the molecule that has the functional group. In this case, is bromine. Again, it's not a functional group, it's a substituent, but I'm calling it functional groups for simplicity. And the same thing here. So I have the same number of carbons, but the difference between my reactant and my product is that the bromine is somehow turning into an aldehyde. Now that I know that the only thing I need to change is a bromine into an aldehyde, I have to ask the question, how do I turn a bromine into an aldehyde? I don't know about you, but I don't actually know how to turn a bromine into an aldehyde. And if you can't think of one step, meaning you can't think of the entire reaction at once, don't look at the entire reaction at once and then ask a different question. If I don't know how to get from my reactant to my product, do I know any kind of other reaction that can give me my product? Meaning, I want you to completely, whoops, not what I meant to do. I meant to do this. Okay. Forget the reactant for a moment. If I had to come up with any molecule that can give me an aldehyde with one reaction, what could that reaction be? Well, how about an oxidation reaction? Where if I have an alcohol sitting on carbon number 1, all I have to do is oxidize that alcohol, and that'll give me an aldehyde. I always save the reagents for last because it's easier for me to come up with this turns into this, turns into that, then go in and fill in the memorized reagents. If you're not comfortable with all the reagents, make sure you go back to the individual reaction videos, and that way you can learn those separately. So I will include the reactions on the side. That way you'll know what you need to go back and review. Now that I know I can go from a primary alcohol to an aldehyde, I have a new problem. Remember, instead of going from A to Z, we want to shrink it down. Let's change the problem now and ask, do I know of a reaction that will take me from a bromine on carbon 1 to an alcohol on carbon 1? Why, yes, I do. All I have to do is swap one functional group for the other, or in this case, swap a bromine for an alcohol. That would be a substitution reaction. Because it's on the primary position, this is specifically going to be an SN2 reaction where I use the alcohol to kick out the bromine, and I'm good to go. So now all I have to do is go through and fill in my reagents. In a substitution reaction, to replace a halogen with a nucleophile, that thing that I circled, that is my nucleophile. So I'm going to need an OH minus. I'll balance it with an Na plus, so I'll put it as NaOH. I want to make sure I get substitution rather than elimination, so I'll put it into a polar aprotic solvent, in this case DMSO. And then for the last step, I want to oxidize it. To oxidize an alcohol to an aldehyde, I can't do a complete oxidation because that would give me a carboxylic acid. And so I want to use the reagent that will do a partial, a mild oxidation, and that is PCC. The trick to remember that we're using PCC, Kevin, absolutely correct, is that, oh, whoops, I hit the wrong one. I meant to do that. Is that PCC starts with P. It's a prude. It doesn't go all the way. It stops at the aldehyde. Question, can we use water instead of DMSO? No. If I switch this to water, to H2O, then I'm putting NaOH in its own conjugate solvent, a polar protic solvent, which would make it favor elimination over substitution. And my product or my intermediate here would look like this, which doesn't help me. Now is not a good time to call. Let me get rid of that. Okay. Which doesn't help me in the case of this reaction. Question, can you use PBr3 instead of NaOH? PBr3 is if I want to go this way. If I have an alcohol and I want to kick it out and put a bromine in its place, PBr3 is one of the reagents that will turn the alcohol into a good leaving group for a halogen. But we're trying to go forward, and so we have to use something with an OH in it. I need an OH to get an OH on there. These are very good questions. Remember, because you're studying for a final, it's not just about this one reaction. It's about everything around it to make sure that you understand how to think big picture and how to tie all the different chapters together. And so this is the warm-up problem, but it's not the only way. In fact, a lot of students will not have learned oxidation in Organic Chemistry 1. Let me know in the comments if you did not cover oxidation. And in that case, let's see if we can come up with another synthetic route to find this product. And the reason I bring this up is not just to show you what to do without oxidation. I want you to recognize that as you learn more and more reactions, you will have more than one option for how to carry out a synthesis. And so if you're going through a reaction, if you're looking at a question and you kind of know one direction, but you're not sure how to see it through, consider another direction. Maybe there's another reaction that you can do that will give you the same product. So in this case, once again, I still don't know how to go from bromine to my final product. I also do not know how to do an oxidation reaction, assuming I have not learned oxidation. What would be another option? What is another reaction that you learned to give you an aldehyde on your molecule? I'm seeing a couple of different comments come in. Joshua, yes, that is the way we want to go. We're not going to go with the reagents just yet, but what you're getting at, Joshua, is I can form an aldehyde from an alkyne. Same 3-carbon chain. But this time, if I have an alkyne, and I'll give myself a little bit more room, I can turn that alkyne into an aldehyde by doing a hydration reaction that will then keto-enol tautomerize. In this case, it'll be an aldehyde rather than a ketone, but that concept of KT, and that will give me the product. So the intermediate here, the initial reaction, will give me something that looks like this. Whoops, did not mean to do that. It'll give me something that looks like this with an alcohol, and the alcohol will tautomerize. This is not a reagent. This is something that happens automatically in this solution to the aldehyde product. And so now we change it up and we ask a different question. Instead of worrying about the product, simplify it. Do I know of a reaction that will give me a bromine going directly to an alkyne? Well, no, I don't know how to turn a bromine into an alkyne, and so that's not going to work. Let's cross out the starting molecule and ask a different question. How can I make an alkyne from something else? If I have the same number of carbon atoms, what molecule can I start with if I want to have an alkyne as my product? Well, how about a double elimination reaction? So this is in the alkyne formation chapter. If I have 2 halogens on my molecule, for example, a bromine and another bromine, I can do a double elimination and get 2 pi bonds forming to give me that alkyne. We're going to need some more room here. And so now we treat this once again as a simpler problem. I don't worry about these anymore. It's a new problem. How can I add a bromine onto a molecule that already has a bromine? How do I add a bromine next to a molecule, next to another bromine on the molecule? This is the new question that I have to ask. And I don't know this reaction because I don't know how to add a bromine onto a molecule next to a bromine. So, well, let's try to find another route. Again, ignore your starting molecule and ask yourself, if I didn't have to worry about my starting molecule, what could I use if I want to have a vicinal dihalide? Vicinal in the same neighborhood next to each other, dihalide, two halogens, in this case, a vicinal dibromide. I know that if I have an alkene, I can do an alkene addition reaction and get the two bromines on there. So that would be the next one to look at. Again, ignore all of this. And now ask yourself, do I know a reaction that will take a molecule with one halogen, get rid of that halogen, and give me an alkene? Why, yes, I do. An elimination reaction. So I want to summarize what I did here because this was quite a few steps. Anytime I could not come up with a synthetic route, meaning I couldn't come up with a reaction that gives me reactant directly to product, I ignored the reaction in its entirety, and I only looked at the molecule I want to form, and I asked myself, how can I form this from something else, keeping in mind that it'll eventually have to start from my reactant, but I worked one step back without looking at the entire thing, and then everything slowly fell into place. And now that everything is in place, I can go forward and fill in the reagents. For the first reaction, we did an E2, where we got rid of a halogen and got an alkene. For this type of E2 reaction, it doesn't matter if I use a big or small base because there's only one option. And so let's use something simple. This had come up before, NaOH and H2O. So now we'll swap the solvent to get elimination rather than substitution. Now that I have my alkene, I want to get two bromines on there. And so I'll react it with Br2. But I want to make sure the solvent does not react. So let's put something inert like CCl4. This is an alkene reaction from the alkene chapter. Once I have both halogens, I can then eliminate, and this is going to be a really strong elimination. So even though it's technically elimination, this is under the alkyne rather than elimination chapter. And for this one, we're going to use something really strong like NaNH2 in NH3 liquid. In NH3 liquid, it's going to deprotonate the terminal hydrogen right there. And so I do want to add step 2 H2O to put that hydrogen back because that's not the reaction we're after here. And then this is another alkyne reaction. We're going to finish this with hydroboration. So you can use any version of boron. A couple of different ones that you'll learn are 9BBN, B2H6, BH3. I think there was one other crazy one that I can't remember the name at this moment. So B2H6, we'll use a solvent THF. That is step 1. Step 2, kind of running out of space here, but NaOH and H2O2. That will give me this, which will immediately tautomerize to the aldehyde, and that's how I get the final product. Same exact outcome, very, very different reaction. If you don't know one method, you just go to the other. Question, would mercury and H2SO4 also work? Yes and no. If I used mercury, I would get a Markovnikov product, and that would put the carbonyl right there. So the product would be a ketone rather than an aldehyde, which is great if you want it in the middle. But in this case, we want it at the end. So we need the anti-Markovnikov product, so we're doing hydroboration. Question, do you need excess NaNH2 to do the double elimination? Yes. So some professors will want you to put excess, the word excess, or the letters X and S, or in this case, it would actually be 3 equivalents, and then water adds the last hydrogen back. These are really good questions, guys. Keep them coming because it's not just about the reaction, it's about everything you can learn around it. Question, why not KOH and heat in the very first step? That would also work. Any small, or not even small, any base for elimination is going to work. Right, so now that we have gone through this from two different angles, let me see some hearts in the comments if you like this approach so far, the breaking it down and figuring out the next step, rather than just attacking the whole thing at once, getting overwhelmed, and not knowing what to do. Let's switch gears for a moment and ask the question, how do you study for something like this? When you covered alkene reactions, you studied alkene reactions. When you did the chapter on alkyne reactions, you studied alkyne reactions. Right now, because you have to study them all, I'm going to challenge you to study by the functional group. And what I want you to do here is just take some time to do a brain dump and ask yourself, what functional group do I know and how do I get there? So let's take an alcohol, for example. If I have an alcohol, how can I form an alcohol? So forget the individual chapters. Let's look at different molecules that can react. I can take an alkene and I can form an alcohol. Depending on which alkene, which reagent, I'll get a different alcohol. I can use an alkyl halide, substitution reaction. I can use a carbonyl, reduction reaction. I can use an epoxide opening. So all of these can give me an alcohol, which is great if I want to do synthesis with an alcohol. I can take that alcohol and subject it to oxidation. And if I oxidize, if I oxidize the alcohol, I can turn it into a ketone, into an aldehyde, into a carboxylic acid. Or go to students, you can take that carboxylic acid and you can turn it into a carboxylic acid derivative. You can go to an ester. You can go to an amide. What am I saying? You can go to just any other functional group. Now, once you have the alcohol, what can you do with an alcohol? Well, we can turn it into an ether. We can turn it back into an alkene, back into a halogen. We can turn it back into a carbonyl, but we kind of mentioned that up there when we talked about oxidation. You can't quite turn it back into an epoxide, but you can take a couple of steps to get there. So do you see how it's not just here's a reaction, here's a functional group, learn all the reactions, here's a whatever, learn all the reactions? You want to be able to look at a molecule and say, how can I make this functional group? And so your challenge for tonight, say yes in the comments if you're going to try it, is to just practice. Take a functional group, turn it into whatever you can. Take one of those, turn it into whatever you can. And that brings up a very good question. What about the reagents? That's the next step. Once you know what you can turn it into, then you want to start practicing, well, how do I turn it into that? If I want this alcohol or that alcohol. And that is a really, really good way to get just a really great handle on all of this. And I am seeing yeses. When you're doing this, you want to look for patterns and clues, because you're not just going to have a file in your brain with all the information. I want you to have patterns where if you look at a molecule and you see a clue, you will instantly know this is the reaction I have to do. This is the reaction I have to do. And that way you're not having to reinvent each problem from the beginning. All you have to do is look for the patterns and immediately recognize what is going to happen. Let's start out with one of my favorite patterns to look for, because this comes up a lot in synthesis. Say you're asked to solve a problem like this, where you have to come up with all the intermediates and all the reagents for essentially what looks like a pattern of moving the functional group. Do you see how the bromine appears to have just skipped on over one carbon on the molecule? What do you think? Is this easy, medium, or hard? And how would you begin something like this? Now we're starting simple, and we'll slowly work up to more and more difficult problems. But for even more practice, I'm very excited to say that about half an hour before logging in, I finally finished writing my brand new synthesis practice exam not available on my website, just comment exam and I'll respond with a link. Yes, even if you're watching the recording, I'll make sure to go through the comments and send you the exam so that you can practice. It's 4 pages worth of just easy, medium, and hard synthesis problems. Here's the thing. We're not actually moving the bromine because this bromine and this bromine are not the same. There is a bromine on the molecule. At some point, we remove the bromine from the molecule and we find a way to put a different one back. So let's go through the steps where we ask the questions. Question number 1, what is the same? And question number 2, what is different? As a reminder, we are looking for the number of carbon atoms, the functional group or substituent on the molecule, and the position of reactivity. Where on the molecule does this take place? And in our problem, we have a total of 4 carbons in the reactant and 4 carbons in the product. So carbon's the same. Substituent / functional group is a bromine, but it seems to have moved from carbon 2 to carbon 1. So the Br on carbon 2 went to carbon 1. And so the question is, how do I move the functional group on a molecule? And the pattern here is very straightforward. You eliminate, you do an addition. Addition, elimination, making it hop along as much as you need. And you'll get quite a few of these functional group moving problems on the practice exam. So let's see what happens. And this one we can take forward. We don't have to go back. Meaning we don't even have to start from the product. I know I want to move it in that general direction. And so the first thing I want to do is eliminate. I want to get rid of the bromine and create an alkene in its place. But the alkene has to be in the direction of where I'm trying to move it. So in the direction of carbon 1. This would be an E2 reaction, but specifically I need the Hofmann product because I want to have the less substituted, less stable pi bond, which is not the Zaitsev product. The Zaitsev product would put the pi bond right here. More stable, not helpful in this situation. Knowing that I need the Hofmann product, I specifically want to use something like KOTB, potassium tert butoxide, in HOTB, tert butanol. And this could be written in many different ways. At heat, just to make sure the reaction takes place. I don't know why I started with the reagents. Let's hold that thought for a moment and show what we're forming. We know we're going to form a pi bond at the less substituted carbon because we needed to move towards the terminal part of the molecule. And then it's just one more step to add a halogen back, an alkene addition reaction. In this case, though, it's a radical addition. So this will be in either the alkene chapter or radical chapter, depending on how your professor taught this. And we have our final product. Now that we have the product, we can go and input in the reagents. I already started giving it to you, so here we go. T-but O-, another way to write it, in T-but OH, tert butoxide in tert butanol at heat. And now that I have the alkene, to get the bromine on the anti-Markovnikov position, that is the radical halogenation, I will use HBr in the presence of peroxides because peroxides are going to give me the anti-Markovnikov through a radical intermediate, and that is what I want in this case. If you're with me so far on the pattern of moving the functional group, let's crank it up a notch. Okay, I'll leave this up for a moment as I draw the next one. For the next question, let's start with a molecule that looks like this, with a chlorine. And somehow, some way, I want to turn it into a molecule that looks like this with an alcohol sitting on the terminal carbon. So study this pattern for a moment. We want to figure out how to move the functional group. But this time, we're moving from a chlorine to an alcohol quite further along across the molecule. First, a couple of questions. HBr and peroxides, yes. And you can use different peroxides. I've seen professors just simplify as ROOR, or even write the word perox to show it's a peroxide, or something specific like CH3OOCH3 or any other R group in there. Question, would Br2 UV add to the third carbon? If you're doing Br2, then that is a reaction you've probably learned with an alkane rather than an alkene. So right now I'm looking for the reaction that will break the pi bond. But if I had an alkane, that is a different pattern that we're going to get to soon. So I want you to hold that question. And I'm seeing yeses and wows. What about heat or light? So this can happen with peroxides or light. Basically, we're trying to find a way to create a radical, to break the HBr apart, and to make this want to reach out for a radical. I covered the exact mechanism in another video. So if you want to review, definitely make sure you watch that. For this next one, let's actually move it to another page so we have room. How would you begin a problem like this? What is the first question you want to ask? What thoughts come to mind? My professor said Chem TV. I'm not sure what Chem TV is. Is that a reference to something or a channel? All right, so we have another move the functional group. So let's start with the questions. You never want to jump right into it just in case the questions give you something more to see. Question 1, what is the same? And question 2, what is different? What is the same is the number of carbons. What is different is the fact that I have a chlorine on carbon 3 that turns into an alcohol on carbon 1. So I have to find a way to move the chlorine 2 positions and somehow in the process also turn it into an alcohol. Am I trying to move it 2 positions? No, no, no. This is a trick. Just because they're written left to right or right to left, don't fall for that. Always number your chain from the lowest side if you're trying to compare. And that means that if I flip this molecule, I'm really just moving the the chlorine from carbon 2 to an alcohol on carbon 1. I'm just moving it 1 position over to right there. This is simply a move the functional group. But by the way, let's also change the functional group along the way. I don't know how to move a chlorine and turn it into an alcohol at the same time. I do have in the back of my mind that this is going to be elimination, addition, as much as I need to get this thing to move over. And so knowing that I want to move it in this general direction, I can start with an elimination to give me an alkene. We'll figure out how in a moment. But if I put the pi bond here, I call this carbon 1, that's this carbon right here, then all I have to do is turn that alkene into an alcohol. Elimination, addition, and the functional group moves over. For the first reaction, we said that would be E2. And once again, because we're moving it to the terminal position, we're doing the Hofmann, not the Zaitsev product. Once I have my alkene, I need an alkene addition reaction. So that is the alkene chapter. And I'm good to go. Let's fill it in. We already saw that tert butoxide in tert butanol is going to give me the elimination with the less substituted pi bond for the Hofmann product. Now that I have the alkene, I need an alcohol at the less substituted position. I need an anti-Markovnikov alcohol product. And in order to do that, just like we saw in the previous example with the aldehyde, we're going to use hydroboration. But for an alkene, you're probably more used to seeing just BH3 rather than B2H6 or whatever other boron reagent. The rest is exactly the same. BH3 THF step 1, step 2 NaOH, and H2O2. And that's it. We are good to go. I know it's going to take a few more problems for this to sink in overall, but how do you feel so far about this approach? Again, I want to hammer this in over and over. Don't start with what you know. Start with just a big picture analysis. What is the same? What is different? How do I make that difference happen? Question, is the addition BH3 THF? Yes, absolutely correct. And I'm seeing a couple more. Question, can you quickly explain how to use the tert butoxide as a reagent? Tert butoxide is an RO-, And so the mechanism here is going to be the tert-butoxide reaches for, let me do this in a lighter color here, reaches for the hydrogen, collapses the electrons, kicks out the chlorine, and you get a pi bond in an E2 reaction. Question. I really like the approach. I just keep getting my reagents mixed up. Nadia, I have some tips on how to, I have some tips for this. Give me a moment on how to memorize reagents. I'm going to add a link into the description. So once this video goes live, I will add a couple of links for you. So make sure you scroll down in the description. And the same for anyone else who is looking for tips specifically on how to memorize the right way. Question. So the first was Markovnikov and this one was anti. Markovnikov gives us a more substitute, the functional group or substituent adds to the more substituted position of the pi bond, which would be here. Anti-Markovnikov adds to the less substituted, which is right here. And that in this case is where we want the alcohol because I want it at the terminal position. So Lawson, I understand it now. Excellent. That's the point of this workshop. That's why I do these sessions, because I want you to have an opportunity to learn in a way that makes it understandable and maybe a teeny tiny bit fun so that you can apply it to bigger picture. Okay, I'm seeing more questions come in. Let's see. Are there certain reactions that appear more free? I can't answer that because it depends on what your professor is trying to test you on or what they choose. Some different professors like different reactions. And so let's hold off on the Q&A. Let's go through a couple more practice problems and then we'll circle back to question. All right, so first let me see some thumbs up in the comments if you feel good about the move the functional group pattern. And then we will look at the next one, which came up before in a question. Starting with something that looks like this. You're given this on your exam, and you're asked somehow, some way, to create a product that looks like, oh, what do I want to put on there? That looks like this. All right. How do we carry this out? Where do we even begin? Question number 1, what's the same? Carbon chain and the carbon chain, okay? Question number 2, what is different? I have nothing on this carbon chain, and here I have a bromine. Now we looked at the number of carbons, which we confirmed is the same. The functional groups, the position of reactivity, and up to now we had a halogen or an alcohol, and we moved it and we changed it and whatnot. But right now, I have nothing. So I cannot apply any kind of a reaction that will change it or twist it or swap it or eliminate it if I have nothing. This is the pattern that I call the something from nothing, because I have absolutely nothing on this molecule. And in order to do a reaction, I first need something on this molecule to react. As soon as you recognize you have a something from nothing, I want you to think of radical halogenation, because the radical is the best way to get some kind of leaving group on the molecule. And once you have a leaving group, you can substitute, you can eliminate, you can do whatever. And someone had asked previously about Br2N peroxides. So let's show that one right here. If I have Br2N peroxides, I will have a bromine adding to the most substituted position, which is, in this case, right over here. This is from the radical chapter. And now that I no longer have nothing on this molecule, it's no longer a something from nothing. Now I simply ask the question, how do I get bromine from this position to this position? Well, if this is a new problem and this is no longer considered, I hope that you recognize our old friend, the previous pattern. Let's move the functional group. Oh, where did it go? Right there. So yes, we'll do a Hofmann elimination so that we have the halogen leave. And the reason we're going to do it as a Hofmann elimination is because I want to make sure the pi bond forms in the direction of where I want to go. I want to go in this direction. So I'll put a pi bond right there. We know how to do this one already. And we know how to do this one as well because we've done this before. So I hope you see how they're starting to repeat. Even though the problems look very, very different, the patterns are the same. So let's go ahead and fill it in. We already know that if we use potassium tertbutoxide, give it to you in a different way so you can recognize it. KOTB and HOTB. This is another way professors like to show it. Then I have my alkene. We already saw that HBr and peroxides will give us the anti-Markovnikov halogen. This is your alkene chapter. This one right here is your elimination chapter. And this one here is your radical chapter. 3 different chapters all came together in one reaction. Andrew, thank you so much. I really appreciate that. Thank you, Andrew. Please email me. I have something for you. All right. So we're looking at what looked like potentially a scary problem, but hopefully you see how, hey, it kind of fell into place. It worked out very, very similar to what we saw before. So if you're with me on this pattern, let me know in the comments, and I will then move on to our professor's favorite. A lot of professors will give you instructions that look like this, starting with ... acetylene. Will give you all sorts of conditions, plus any other inorganic reagents. Synthesize, and they'll come up with some crazy molecule. I will keep it simple just to show you the patterns, but I have some more difficult ones in the exam. And again, just comment exam, and I will give you a link to my brand new synthesis practice exam pages, quite a few pages of practice problems. And we have to figure out how to do this. So first, we start with the questions. Question number 1, what is the same? And question number 2, what is different? Well, what is the same as what? What is different as what? We don't have anything here. So what exactly are we going to compare? Well, we're told to start with acetylene. So we'll use acetylene. And that is, you should know this name. You should know what it looks like. This is an alkyne, great for chain elongation in Orgo 1. Orgo 2 students, Grignard's tends to be my go-to, but it also depends on what else, what it is that you have to form. So in this case, now that we have a starting molecule, what is the same and what is different, I'm going to look for 2 carbons on my product and then see what else to add. So I can choose these 2 carbons, or I can choose these 2 carbons, and I want to be strategic in how I choose it. What I'm looking for when choosing where the acetylene or where the aldehyde winds up, I want to ask myself, what functional group do I have on this molecule that could have come from, at some point, an alkyne? And I see that I have an aldehyde, which definitely could have come from hydroboration of an alkyne. So I know that that's where I have my 2 carbons. And this means that if carbon 1 and 2 came from my acetylene, I have to add +1 carbon, and that will be specifically carbon 3. And the question is, how do I add that? I don't have to answer that yet. Instead, I'm going to work backwards and ask myself, if this came from an aldehyde, I'm sorry, not an aldehyde, if this came from an alkyne, from my acetylene, what would this have looked like before it was the aldehyde? What would it have looked like when it still had the alkyne? So we'll go one step back and we'll say these 3 carbons, why am I drawing it like that? I meant to draw this right here. These 3 carbons would have looked like this. And yes, I want you to draw it like this. I do not want to see you drawing it like this. Alkynes are sp hybridized on that alkyne carbon. That is 180 degrees. It's got to be linear. I've seen professors do it like this, and it makes me cringe. So we have the alkyne. We know that one quick reaction will turn it into the aldehyde. Well, technically, it'll turn it into this right here, but it will not be isolated. It will immediately tautomerize via ketoenol tautomerization. And so I am good to go here. And now, if I know that this is my acetylene, then if this is my new bond, all I have to do is add a leaving group there. As soon as you identify what connects to the alkyne, give that a leaving group. And as soon as you do that, you know you have an SN2 reaction. I'll put it SN2, but really this is something that you learned in your alkyne chapter. And so all I have to do is, well, first I have to activate my alkyne, and I'll activate it so that I deprotonate the terminal hydrogen to give me HCCCC lone pair negative charge. Now I want to react it with whatever I'm adding, which in this case is just one carbon. So I'll put it as a CH3, give it a leaving group, we'll give it a chlorine, and that's it. I have my acetylide. It attacks via SN2 reaction. I get my alkyne. I then react it to get the aldehyde. So let's put in our reagents. What do we have here? NaNH2. Remember I said earlier that once the alkyne forms, another one will deprotonate. This is an NH3 liquid. This will happen whether you wanted to or not in that previous reaction. And so in this case, it works out. But if you add water, you destroy it. Once I have my acetylide, I react it with this. That's just an SN2 reaction right there. We already saw this next one. We used B2H6. THF, it's kind of on there, but we saw it before, so it's okay. You already know. NaOH, H2O2, and we're good to go. My last semester professor took off points because I drew 180 degree for what? How? I don't know how to teach, so I'm going to deduct points because you learned how to do it the right way. What is that? Come on. Quanta, I don't know what you're referring to. Right, so any questions on this one? Go ahead and type it in. Okay. If you got the different patterns that I showed you, and you're ready to tie them together into a trickier problem, go ahead and type "bring it on" in the comments. And then for even more practice, as a reminder, make sure to try the brand new synthesis and multi-step reactions practice exam. It's not available on my website. All you have to do is comment exam and I'll respond with the link. Yes, even if you're watching the recording. I see the bring it ons, so let's bring it on with, and I want you to tell me at first glance if this looks like an easy, medium, or hard question. Given a starting molecule that looks like this, somehow, some way, you need to figure out how to synthesize something that looks, let's help. It helps if I don't draw it completely drunk like this, using, well, whatever you want, as long as you come up with the product. So where do you even begin for something like this? Question, do we need to take into account equivalence for this mechanism? Yes, if your professor asks for it. So you're asking about this one. In this case, let me see. Just one equivalent to deprotonate, one equivalent to add. No, this is all one equivalent, so we don't have to. But in a previous one, I know I had it somewhere. The one where I think it was Nadia had asked about excess. It was one of the earlier questions we did, where if you have to use more than one, you can either write excess or you can write how many equivalents are necessary. Keep in mind that if you want a reaction to do a partial, meaning if a reaction would automatically use 3 equivalents, but you only put 2, you're not necessarily limiting it in the right way. So let me detour for a second to explain that, because that was a really good question on equivalence. Let's talk about it right here. If I have an alkyne, let's just do a very simple alkyne reaction. And I know that reacting this with HBr in excess and the appropriate reagents and the appropriate solvent, will give me both pi bonds being broken, where when the first pi bond breaks, I get an H and a Br. And when the second pi bond breaks, I get another H and another Br. I have seen questions where, and this is actually a good synthesis problem, where the professor will give you the alkyne and ask you how you can synthesize an alkene. No, I'm trying to think. Oh, you know what? This is the problem right here. Something like this. And what some students will try to do is limit the number of bromines, or there's another one that is not coming to mind right now that students will often confuse. But what I'm getting at, let me remove this for a moment. What I'm getting at is if I don't use excess in this case, I will not stop in the middle, because what will happen is of 3 molecules that are here to react, if I try to limit the equivalent, so let's say I only put in enough HBr so that each molecule gets 1. I'm not going to have partial reductions the way, partial additions the way you are expecting. I'll have 1 molecule that has the product as expected. So this one is using up 2 of the equivalents. I'll have another molecule, and I don't mean 1, I mean hundreds and thousands in this ratio. We'll have just 1 because it ran out. And then I'll have a bunch more that just never got anywhere, because 1 equivalent doesn't necessarily tell them all, hey, you all better only use 1. They're not very good at sharing. Some will grab them all, some will get none, some will get stuck in the middle. All right, who had asked that question? The chat scrolled. Okay, for whoever asked that question, let me know if this makes sense regarding equivalence. So the way to control a reaction is not through equivalence, it's through making sure you use the right intermediates, the right sequence of events. So let's jump on over to this problem, starting with our 2 questions. Question number 1, what is the same? Question number 2, what is different, and how do I bring about that change? I have a carbon chain, not what I was trying to do. I have a ring that doesn't change. What is on the ring here? I have 1 carbon. Why does it keep doing that? 1, that's 1. But then I have carbons 2, 3, and 4. So what's different here is I have plus 3 carbons being added and a pi bond, specifically in a cis conformation. And that pi bond was not accidentally drawn as a cis. It has to be, we have to make sure the product goes cis. So where do I begin something like that? I have to consider, first of all, how do I add carbons to the chain? In Organic Chemistry 1, the most direct way is to add an alkyne for chain elongation. And then I want to make sure I reduce it the right way. You are absolutely correct. You are on fire. So let's take it step by step. Knowing that chain elongation comes from an alkyne, let's work 1 step back and say that this had an alkyne. 4 carbons coming out of the ring. I do not want to draw that ring over and over, so let's do that. 4 carbons coming out of the ring, 1, and then the alkyne is attached to that. So 2, 3, no, that is in the wrong spot. Hang on, let me draw that correctly. 1, 2, 3, 4, like that. So that is carbon 1, 2, 3, and 4. 2 and 3 is where the pi bond is, but I have my alkyne going to an alkene. And as soon as I identify the location of the alkyne, recognize that this right here is going to get a negative charge. This right here gets a leaving group. That is how you undo a chain elongation without mixing up where the pieces came from. And so one step back, let's give ourselves a little bit more room here. Here we go. So one step back, I'm going to take off that alkyne and put a leaving group because we said we need a leaving group if we're taking off the alkyne. So what does that look like? We have our ring with only one carbon on it. We'll put a bromine because why not? And then, even though I don't like to put in the reagents, I do want to make sure I account for this. So those 3 carbons, I will simply put as deprotonated 3-carbon alkyne negative charge, which now means I don't have to look at this entire reaction. I just have to figure out this. I have nothing on my molecule. I need a bromine because I need a leaving group. This is the something from nothing reaction, which we've already looked at. This will be a radical halogenation. And for halogenation next to a pi bond, for example, if you have an alkene or a benzene ring, you may see HBr and peroxides, but typically your professors are going to be looking for NBS, N-bromosuccinimide. This is kind of like a radical babysitter, and it puts the bromine via radical mechanism on the carbon directly next to a pi bond, so allylic or benzylic. Can we use, let's see until alkylation happened. Quanta, let's stick to the questions here. And so now that we have most of the pieces in place, let's confirm we have all the reagents. The first one is a radical reaction. NBS is a way of doing radical bromination. N-bromosuccinimide, the B is bromo. That's how we get the bromine on there. Once we have a good leaving group, we have an SN2 reaction. So this would be SN2, but it's also something that you likely learned in the alkyne chapter. The last step, we want to be very careful to make sure that we do it the right way. If I have an alkyne and I want a cis alkene, I can't just use any reduction. I have to specifically use H2 in a Lindlar's catalyst, because the Lindlar's catalyst is a poison metal catalyst. It's slow down. It's not going to reduce it all the way. And specifically, it's going to grab the pi bond from the same side and push the groups next to each other when it breaks away one of the pi bonds. And that's how we get our final product as a cis alkene. Is it wrong to use Br2 and peroxides? No, I've seen Br2 and peroxides used in this situation as well. I put NBS because a lot of students will see this, and I want to make sure that you know to recognize it. And we've already done Br2 with peroxides, but that's a really good question. I wrote many, many more practice problems for you, and they are all in the synthesis and multi-step reactions practice exam. If you haven't already, comment exam, I'll respond with a link, and that way you'll be able to continue practicing. A copy of all the session notes, everything that I wrote today, go to layerforsci.com/orgolive. And when you sign up there, you will get access to all PDF notes from all the different live streams that I've done. So that includes the session notes from today, as well as any of the other topics that you watch on my YouTube channel.